In section 2.1, Understanding Scientific Notation, students will understand the need for scientific notation. Students will write numbers in scientific notation or in standard form. Students will compare numbers in scientific notation. Let's just quickly go over what is scientific notation. Sometimes you have numbers, standard numbers, 125, let's say, right? It's a simple number, very easy to write, very easy to read. But then you got numbers like the distance from Earth to the sun. That's a very, very, very big number. And of course, I wouldn't be able to fit that number in a small spot. So what we do instead is we convert very large numbers into scientific notation so that it's easier to read as well as easier to write. Let me make one thing clear too. It works for very large numbers, but it can also work for very small numbers. And I'm not talking about negatives. I'm talking about like the size of an atom. So even numbers that are extremely small, scientific notation works very well. Just some vocabulary words to go over. Scientific notation is the way that scientists easily handle very large numbers or very small numbers, is what I just said earlier. Coefficient, a number or symbol multiplied by a variable or an unknown quantity in algebraic terms. So for example, 5x, the coefficient number for 5x is 5. And 7y, the coefficient number in 7y is 7. Once again, the number that's being multiplied by a variable is called a coefficient number. So in this case, right, it's really 5 times x. That's why the 5 is the coefficient number. In the second example, it's 7 times y technically. So that's why the 7 is the coefficient number. And then standard form, it's like your basic number. Any number you can think of. 125, like I said before, that's standard form. 78, that's standard form. I'll read the definition, but you'll see what I mean. Standard form is a way to write numbers using the digits 0 through 9. So like you see how this is 0 through 9, this is 0 through 9, and this is 0 through 9, as well as this is 0 to 9, and this is 0 to 9. So standard form is just the numbers that you're used to seeing. Scientific notation will look more like this. But scientific notation will be like 7.2 times 10 to the 4th power. That is scientific notation. 7.2 times 10, and they'll say to the 5th power. Once again, this is an example of scientific notation. Let me explain what this is all saying. So the A is this guy right here. So the number that's before the multiplication symbol. That number here represents the A. And what it's saying right here is A has to be either equal to 1 or no bigger than 10. So pretty much any number that's exactly 1 or slightly smaller than 10 is what your A has to equal to. And if you look at my example, 7.2, isn't that between 1 and 10 technically? Once again, it could equal 1, it just can't equal 10. It has to be like 9.9999. And 7.2 is in between those two numbers. You always have a power of 10. This is an always thing. No matter what my example is, I'll come up with another one right now. 5.1 times 10 to the 4th power. Once again, notice how my A is between that 1 and 10 that I mentioned before. And notice how my base 10 is still base 10. I always have a base 10. Always. And then the exponent, they call it the n, which represents an integer. An integer is just a number without a decimal or a fraction. 5 and 4 are both integers. Scientific notation is A times 10 to the nth power. A has to be any number between 1 and 10. It can equal 1, but it cannot equal 10 though. It has to be slightly under 10. The base 10 is always, so it's always times 10. Okay, so let's read this example together. Example 1. Tell whether each number is written correctly in scientific notation. If it is incorrectly written, state the reason. So once again, if it's right, awesome job. If it's wrong, then you just gotta say why. So a horse chestnut has a diameter of about 2 times 10 to the 0 power centimeters. All they want to know is this written correctly in scientific notation? Well, first thing is my A, which in this case is 2. Is it between 1 and 10? Once again, it can equal 1, but it has to be slightly under 10. Yeah, right? Isn't 2 definitely between those two numbers? So the A is good. And then times 10, right? It's always times 10. And even 0 is an integer. So yes, actually this is written correctly. Right? Let's try the next one. Neptune is about 4.488 times 10 to the 9th power kilometers from the sun. Once again, my A, is it between 1 and 10? where it could equal 1, but it has to be slightly under 10? Yeah, 4.488 is obviously somewhere in the middle of 1 and 10, so that's good. It has that times 10, right? Not times 5, not times 15. It has a times 10. And even our exponent is a number without a decimal fraction. So this one's also good. The approximate wavelength of infrared light is 0.01 times 10 to the negative 5th meter. So this one, unfortunately, is not written correctly. And I'll write my explanation here. 0.01 is not in between 1 and 10, where it can equal 1, but not 10. That is my answer for letter C, right? It was a no, and that's the reason why. My A was too small, right? The smallest A can be is 1. Maybe that's another good way of phrasing it too. The smallest number A can be is 1. The biggest number A can be is slightly under 10. So 9 point and then like a billion nines. It just can't be 10. Hint, hint. Try this one on your own. Right? I said hint, hint for a reason. Let me know if this is written correctly in scientific notation. If it's not, please explain why. Hint, hint. Hint, hint. Maybe use the same wording that I have here. Hint, hint. Okay, and then you'll do these guided practice as well. It's the same thing as before. Just tell me if it's written correctly or not, and if it's not, please explain why. Focus mainly on the A. All right, example 2. Write each number in scientific notation. Step 1, figure out your A. Your A has to be between 1 and 10, right? It can equal 1, but it can't equal 10. So I want to place a new decimal where I can make this number in between 1 and 10. If I place the new decimal here, that'll be 42.77. Still too big. If I place a decimal here, it'll be 0.4277. That'd be way too small. However, if I place a decimal right here, my new decimal, it'll be 4.277. 4.277 is in between 1 and 10. So my new decimal has to be between the first two numbers that I see. So now I'm going to rewrite it where the new decimal is. So all I'm going to do now is rewrite the problem. 4.277 times 10, right? Because scientific notation is always times 10. And then to get the exponent, I just count the spaces from the new decimal to the old decimal. So it's going to be a 1, a 2. There's 2 spaces between the old decimal and the new decimal. So my exponent is going to be 2. And that is how you convert standard notation to scientific notation. One thing I want to explain too, notice how my exponent's positive. The reason my exponent was positive was that because my original number was greater than 1. Whenever your original number is bigger than the number 1, you always have a positive exponent. If you notice here, we're going to be converting this number into scientific notation. That number is smaller than 1. Because it's smaller than the number 1, I'm going to actually have a negative exponent. Everything else is the same, but my exponent's going to be a negative. Once again, everything else is the same. Where would I place my new decimal so that now it's between 1 and 10, right? If I place a decimal here like a lot of kids think, they will be wrong because that's 0.7. That's still like 70 cents. That's still under 1. You want it to be between 1 and 10. Only position you can place the decimal so that it's between 1 and 10 is actually at the end of the number in this case. Now that would be 7 point, and I can add a 0 if I wanted to. 7.0 is in between 1 and 10. So now I'm going to write 7.0. I don't need to worry about any of this. Times 10, like we always said before. And then to get the exponent, I'm still going to count the spaces from the old decimal to the new decimal. So here's going to be 1, 2, 3. So my exponent's going to be 3. The only additional step now is, once again, here, my original number was bigger than 1. So my exponent was positive. Here, because my number is smaller than 1, my exponent will not be positive. My exponent will be negative. My final answer, 7.0 times 10 to the negative third power. All right, try this one on your own. You're to write both of these numbers into scientific notation. Please make sure you put a negative with the exponent if you need to. Once again, you know if an exponent is positive or negative based on the original number. If the original number was greater than 1, it's a positive exponent. If the original number is less than 1, it's a negative exponent. All right, part B. Write each number in standard form. 7.1 times 10 to the third power. So now we're doing the opposite, right? Before they gave us a standard number and we had to convert to scientific notation. Now they're giving us a number in scientific notation and we got to go back into standard form. Standard form is like the typical number that you're used to. 7.1 times 10 to the third power. Below it, I'll just write my A, right? So the first step I'm doing is I'm running my A. My A is 7.1. And then, remember, this guy right here tells me the spaces. Remember from before? If it's a positive exponent, you're going to move it to the right. If it was a negative exponent, you would obviously move it to the left. But because this is positive 3, we're going to move it to the right, right? We want a bigger number. So obviously we want the decimal to go to the right so that it increases and not decreases. So now I'm going to take my decimal and I'm going to move it 3 spaces to the right. 1, 2, and 3. Because I don't have any numbers here, I could put zeros as placeholders. My final answer, and you have to rewrite this. I have some kids do this and they circle it. Oh, I'm done. You have a number that has 2 decimals in it. No. Your number is 7, 1, 0, 0. And if you want, you can put the new decimal at the end. But I can't have this as my answer because I need this to go away. Remember, this decimal moved to the right 3 spaces. It can't be there anymore. That's why you have to rewrite it. You can put a comma there so you know it's 7,100. But you don't even have to do that if you don't want to. This is your final answer. So now we got to convert 8.12 times 10 to the negative third power into standard. Same thing as before, I first rewrite just my A. So my A is 8.12. And then this guy is telling me how many spaces to move the decimal. This time though, my exponent is negative. So I'm moving it to the left and not the right. So I'm going to take my decimal and I'm going to move it 3 spaces, but this time to the left. 1, 2, and 3. I put zeros as buffers. Once again, I rewrite this. I don't circle this. This is not my answer. So I rewrite it. I have a decimal. I have 2 zeros after the decimal. And then I have the 8, 12. And there's my answer, right? Do these 2 on your own. Don't worry about this squiggly line. These are actually 2 problems. If you want, you can separate it with a line. Convert this into our standard form and convert this into our standard form. All right, part C, example 4. Compare numbers in scientific notation. Identify the greater number in each pair of numbers. Justify your reasoning. Both of these are actually part of the same problem. They just want to know which one's bigger. So I'm going to rewrite it. A little trick here. You can convert both of these into standard form if you want. If you convert both of these into standard form, obviously the one that's bigger is your answer. So I'll just do that real fast. So this is telling me to move the decimal 2 spaces to the right. 1, 2. So it's 560. And this is telling me to move the decimal 1 space to the left. So it's 0.34. And then obviously which one's bigger, 560 or 0.34. Then you go $560 versus 34 cents. This is the bigger number. But there's actually a fast way, believe it or not. And the fast way is when both numbers are already in scientific notation, just compare the exponents. Which one's bigger, 2 or -1? Right? Obviously 2 is. So I know for a fact that 5.6 times 10 to the second power will be bigger than 3.4 times 10 to the negative first power. There is only one catch to this. If the exponents are the same. So if the blue had an exponent of 2 and the red had the exponent of 2 as well, they're not equal. If the exponents are the same, then and only then would you have to compare your A's instead. So that's the only catch to it. First, check the exponents. The one with the bigger exponent is always the bigger number. But if the exponents are the same, before you can answer it, you got to check the A's. If the A's are the same, then the whole thing's equal. But if the A's are different, then obviously the one that has the bigger A is the bigger number. Hint, hint. Do you see here how the exponents are the same? So try figuring out what I just said before. So go ahead and do this on your own. Tell me which one is bigger. And here, tell me which one is bigger. All right, compare a number in standard form with a number in scientific notation. In 2000, Americans consumed an average of 47.2 pounds of potatoes and 5.936 times 2 to the second power pounds of dairy products per person. Did Americans consume more potatoes or dairy products? So obviously the word problem is asking which one's greater, which one's more. So this is no different than what we just did in the last example. So I'm going to write down both problems. So you got 7.2, and that represented the potatoes. So I'm just going to put P there, right? For potatoes. And then you had another number that represented dairy products. So dairy, and it's 5.936 times 10 to the second power. Now, in order to see which one is bigger, you got to compare an apple with an apple. One is in standard form, and the other one is in scientific notation. So you either have to convert both of them into scientific notation, or to convert both of them to standard form. It is up to you which one you want to do. Me, I think it's easy to convert both into standard form. So that's what I'm going to do, but you can do either one. So I'm going to convert the dairy into standard form. This is telling me to take my decimal and move it 2 spaces to the right. So 1, 2. I'm going to rewrite my problem now. My decimal is now in between the 3 and the 6. So it's 593.6. And I'm comparing that to 47.2. Obviously, which number is bigger? The 47.2 or the 593.6? Right? Obviously, the 593.6. So your dairy product is more, right? Did Americans consume more potatoes or dairy products? Final answer is they consume more dairy products. Try this on your own. It's the same thing as before. They're asking about which one's more. Compare an apple and an apple. Either make them both scientific notation or make them both standard form. It doesn't matter. Here, same thing. So you're going to do it on your own. Just be careful. Here they're asking about which one is shorter. So you're doing what I just said before, but this time they want to know which one's the smaller number and not the bigger number. So read the whole thing on your own. Just know once again, they want the smaller number. And once again, you can do this one. And this one is asking for which one is bigger.